to Physics Society and welcome to the second talk this Nicholas term. For those of you who are new, welcome. My name is G and I'm the President. We're joined today by members of the committee, Rob, who's our IT officer, Alex, who's our treasurer, Arda and Akash, who are our academic officers, Vivian, who's our innovation director, and Roxanne, who's our secretary. Welcome, and we're delighted to welcome our speaker today, Joseph, for his talk on digitalising physics.
Thank you. Yeah, and thank you for... Thank you. Yeah, so thank you for having me. Yeah, I'm going to talk about digitalising physics, which is... I'll explain what this means in a second. You can scan the slides, or you can scan this to see the slides. I warn you, there's a slide that looks a bit odd if you scan it. Don't worry, it's meant to be there. You'll see it in a second. And you can also just visit josephtooby-smith.com/slides/Oxford, which is where we are in 2025. There is a point on this where I really do recommend you, download the slides and interact with them as we go along. So, yeah, I'm going to speak to you about digitalising. Oh, have I turned my microphone on? Okay. Yeah, so I'm going to talk to you about digitalising physics. And the talk is going to be split into three parts. The first part, I'm going to talk to you about what an interactive theorem proofer is. You don't probably know what that is, so I'm going to explain what it is, what you can do in it. The second part, I'm going to introduce you to this project called PhysLean. And then in the third part, I'm going to tell you how you can get involved in this project if it's something that interests you. If you're watching this and you're thinking, maybe this is something that I could do. So, yeah, I want to start by telling you what an interactive theorem prover is. But to do that, I want you to put yourself back to July 19th, 2024. So July 19th last year. On this day, you probably woke up, you probably opened your laptop, and everything probably worked fine. But about 8.5 million people were doing the same thing, and things didn't look fine. They saw this. This is called the blue screen of death. It happens in a Windows computer when a program crashes in the kernel of the computer and Windows can't escape it. This specific incident was down to some malware software that was working in this kernel of Windows computers. The malware software had a mistake in it, and Windows couldn't close it. This shut down airports, it shut down hospitals, and it shut down governments. So if you weren't directly affected for it, you may well have been indirectly affected by it. The company that caused this became infamous, and this was called the CrowdStrike incidents. It was down to a logical error in some code, a mistake, a bug. If you've ever done any programming as part of your undergraduate course, maybe in your labs, you have probably experienced these sorts of bugs. They are mistakes in code. Why am I telling you a story about code in a talk about physics? Well, that'll become apparent in a second, but I want to tell you another story before I explain. Who here has made a sign mistake or a factor of 2 error in a problem set? Yeah. Basically, everybody in here has probably made such a mistake somewhere along their academic career. And you'll be glad to know that such mistakes are not restricted to undergraduates. They happen in research level physics as well. And to give you an example of that, I want to tell you my second story. This is a story about an archive paper. And this is just the number of the archive paper, HEP-PH 0512212. Archive is something called a preprint server. It's where you put papers before they become published. And I want to tell you a story about this paper, a QCD summary study of light scalar mesons. I don't expect you to know what this means. QCD is basically the area of physics that governs the strong force, and mesons you may have come across if you've done particle physics. They're a type of particle. The author of this paper, Hee-Jung Lee, calculated this quantity E. And he did this by adding together some terms, A1, A2, A3, up to AN. I want to tell you what happened after this paper went on the archive. Because shortly after this paper on the archive, went on the archive, another paper appeared. A comment on the QCD somewhat study of light scalar mesons. And what this comment said is it said that this paper had made a mistake and that it had missed two terms, this B1 and B2, that suddenly appeared in my equation. And then when added to this quantity E, invalidates the conclusion of the original paper. Shortly after this paper, this comment appeared on the archive, another paper appeared. A reply to the comments on the QCD somewhat study of light scalar mesons. When you start getting replies to comments on the archive, you know the boxing gloves are really coming off, and these people are having a proper argument in the academic forum. The comment was by the original author of the first paper, and this reply, and the reply said those terms shouldn't be there. The comment was wrong, and the original paper was correct. Shortly after this reply to the comments appeared on the archive, another paper appeared. A reply to the comments on a QCD somewhat study of light scalar mesons, saying those terms should be there, and the original paper was wrong. The conclusion to the saga was that the authors of the comment and the reply to the comment realized that they had made a mistake. They had made a typo error, something like a factor of 2 error or a minus sign error. In this case, it was slightly more conceptual than that, but it was of a similar variety. This wasted the research time of 4 academics over the span of around 6 months. That is research money, that is taxpayers' money spent to have an argument where the conclusion was that somebody had made a mistake. So I told you these 2 stories, and you're probably wondering why on earth have I told you 2 stories that seem naively very different. Well, these 2 stories are really different manifestations of the same problem. If you think of Microsoft Word or LaTeX, which is what academics use to write papers, or even your pen and paper, if you think of that as a programming language, and this is a bit of a stretch, but go with me here. If you think of that as a programming language where you write down definitions and you write down theorems, you can think of minus sign errors, factor of 2 errors, as the same thing as bugs in code. And if you take that approach, if you take that thought process, you can see that these 2 stories, bugs in code, minus sign errors, factors of 2 errors in papers or in problem sets, are really different manifestations of the same problem. And it's not helped by the following. So this is the text box, and I'm going to write something into this text box. You can think of this text box as being akin to Microsoft Word or akin to something like LaTeX. If you know what LaTeX is, it's basically what academics use to write papers. If you don't worry. So I'm going to write something into this text box, and we're going to see what's going to happen. So I'm going to say, let f be a function from nat, the natural numbers, to nat, the natural numbers, and let a be an integer. Then f is equal to a. So, you will notice one thing. I have made a typo. I have made a spelling mistake. And you will see that LaTeX, or Microsoft Word, is clever enough to spot that spelling mistake. It has put a little squiggly red line under it. So let me fix that, and we'll see what happens. So fix that typo, and you'll see that Microsoft Word, or LaTeX, thinks that this sentence is absolutely fine. If you know anything about mathematics, if you think about this sentence in a bit more detail, you'll realize that it makes absolutely no sense whatsoever. You can't set a function from the natural numbers to the natural numbers equal to an integer. It doesn't work. It doesn't make sense. It's like saying the function that takes a natural number and squares it is equal to 3. You can't do this. But LaTeX doesn't know that. Microsoft Word doesn't know that. Your pen and paper, when you're writing your problem sets, doesn't know that, it will happily let you write down things like this, and it will happily let you make these sorts of mistakes. But what happens if that wasn't the case? What happens if Microsoft Word or LaTeX or your pen and paper, when you're doing your problem sets, what happens if it knew that you couldn't write this down? What happens if it knew that you couldn't make these sorts of mistakes? In other words, what happens if there was a way to guarantee that your code was bug-free, or that your problem sets were free of minus sign errors or factors of 2 errors? In other words, what if there was a way to guarantee that you knew what you wrote down was mathematically correct, that you hadn't made any of these errors? Well, you can probably guess by the title of this talk that there is a way that you can do this. And this is to use something called an interactive theorem prover. So, I'll explain what an interactive theorem prover is in a second. It is a programming language. It is something like Python or C++ or Fortran. It is something like LaTeX or Microsoft Word, if you're willing to think of those as programming languages. But it is a programming language where you can't make mistakes, or at least certain types of mistakes, because it will tell you that you've made those sorts of mistakes. There are some popular interactive theorem provers out there, and here are a list of a couple. Most of these I expect you have never heard of, but I will explain what they are in a second. So there is this one called Rock, there is Isabelle/Hall, there is Lean, and there is something called Agda. If you've heard of any of these, you probably have heard of Isabelle. Isabelle is a programming language that people use kind of generally, but it is one of these types of programming languages called an interactive theorem prover. I'm going to focus on Lean for this talk, but everything I'm going to say is kind of generically true for all of this. So I thought I would give you an example of what these programming languages do. At this point, I would recommend, if you're interested, you follow along by following this link down here, because then you can, it's slightly more engaging than just watching me type stuff. So the first thing I'm going to do is I'm going to write down the same sentence that we wrote down at the start a couple of slides ago, and we're going to see what Lean does. So there's going to be some syntax involved, but I'm going to write down, and hopefully you can see this, complain if you can't. I'm going to write down an example. We're just going to do an example, and this is just some syntactical sugar. And we're going to say let f be a function from the natural numbers to the natural numbers, and let a be an integer. Then f is equal to a. And we're just going to finish the line by this by sorry thing. You don't need to know what that means. It's just kind of saying we're not going to provide a proof of this. But you will notice something. In the same way that Microsoft Word gave us a squiggly line when we made a spelling mistake, Lean gives us a squiggly line under this a. So here I've said let f be a function from the natural numbers to the natural numbers, let a be an integer, then f equals a. Lean knows you're not allowed to write this. Lean knows that this doesn't make any sense. And if we hover over the a, it says something that might be a bit cryptic. It says there is a type mismatch. You don't need to know what a type is. It says that a has type z, so a is an integer, but it's expected to have a type the type of a function from the natural numbers to the natural numbers. And you're not allowed to equate these two, because that would be akin to equating the function that squares a number to the number 3. And that doesn't make any sense. And Lean knows this. And notice that it knows this as I am typing it. It's not something I have to compile. It's not something I have to get it to run. As I am typing this, it gave me this error. So hopefully you can see the potential use of this. I'll show you a couple more examples in what follows. But if you have something that stops you making these sorts of mistakes, then you have a way to write stuff down and be guaranteed to know that what you've written is correct. So to give you a better understanding of how these interactive theorem provers work, I thought we would do something very simple. And I should say that if you get lost for the next bit of the slide, don't worry. It's not relevant to what I'm going to say in future slides. It's to kind of just give you an idea what these interactive theorem provers look like, but you can come back into the talk after I have said what I'm about to say on the slide and about what I'm about to demonstrate. So we're going to define the natural numbers. So Lean is based on this thing called type theory. A type is very similar to something called a set. A set is basically something which has elements, like the set of real numbers has the real numbers as elements. The set of integers has integers as elements. The set of natural numbers has natural numbers as elements. So we're going to define the type of natural numbers, and we're going to do it inductively. So I'm going to write this down here. Ooh. And Lean will always give us an error if we do something wrong. So we're going to define the natural numbers in Lean by specifying what elements it has. So what elements do the natural numbers have? Well, the first element is 0. So we can write 0 is a natural number. I'm using MyNat just to not have a confliction with names, but we can just think of these as natural numbers. So this is the set or the type with one natural number corresponding to 0. That's not the set of natural numbers. We have to specify them all. So we can give it the natural number 1. We could go and give it the natural number 2. And, you know, if I had all day, I could go and I could be here and I could write down all of the natural numbers. And that would define the type of natural numbers. But you can do things in Lean, you can do things simpler than that. You can define things inductively. So you can go for every natural number, so that 0 is a natural number, and then for every other natural number, you have a successor of that, which is that natural number plus 1. So you've got 0, and then you've got a successor of that, which is 1. 0 plus 1 is 1. But now you've got 1, so you have a successor of that, so that gives you 2, and so on and so forth. So this allows you, so you can define the natural numbers as the following. You can say you have 0, and then you have the successor, which takes in a natural number as a function and gives out a natural number. And this is the definition of the natural numbers. This is like 0, 1, 2, 3, 4. This is how they are defined in one of these interactive theorem provers. And once you've got a definition like this of a type, you can start to construct other types. So you can start to construct the type of functions from natural numbers to natural numbers. And you can make mathematical definitions. So the definition of addition is an element of the type of functions from natural numbers to the function of natural numbers to natural numbers. It is an element of the set of natural numbers, of functions from natural numbers to the functions of natural numbers to natural numbers. In other words, it is something that takes two natural numbers and outputs another natural number. And we can define this in Lean. And we can define it as follows. So we can say that addition takes 0. Oh, let me put a dot there. It takes 0, and it takes a natural number n, and that gives us n. So 0 add n is equal to n, and I'm getting a squiggly red line because I haven't done the other case, which is when this first natural number is not 0, but it's the successor of another natural number. So it's not 0, but it's like n plus 1, where n is another natural number. So if you've ever learned proof by induction at school, this is basically very similar to this. So we can go the successor of a natural number n is equal to the successor of the addition of m and n. And hopefully it will work. Good. So yeah, this is how you would define addition in one of these interactive theorem provers. And you can define multiplication in a similar way. Notice that the definition, that the statement of the definition is used in the definition itself. This is something you may have heard about in programming languages called a recursive definition. Lean is clever enough to work out for itself that this function terminates, so you don't have to worry about, does this terminate or not? Lean works it out for you. You can define multiplication in a similar way. I'm not going to do that because for time, but yeah. But so you can write definitions, and these definitions are computable. So like in Python, you can add two numbers. You could say, or like Mathematica, or things like R, you could take two numbers, you could take 2 and 2, and you could go, what is the addition of those natural numbers? You can do that in Lean. So Lean is the same as like Python or C++, in that you can execute these functions. So I can go, let me add the successor of 0, which people have probably told you is called 2, because that's 0 add 1 add 2 is equal to 2. And we can add that to itself. The notation here is a bit weird, but I'm just evaluating 2 plus 2. And hopefully you will know that 2 plus 2 is equal to 4. And you can see the answer here on the right-hand side of the screen. And it's equal to 0, add 1 successor, add 2 successor, add 3 successor, add 4. 2 plus 2 is equal to 4. And you could do the same with multiplication. But you can also, so not only can you execute these functions, but you can also prove theorems about them. So we're going to prove a theorem in Lean. And again, the main benefit of this is that Lean will guarantee us correctness of our proof. It's not going to let us make, a slight mistake in it. We might not, Lean will not let us make a -2 error. For example, Lean will make sure whatever we write down is absolutely mathematically correct. So the thing we are going to prove is that, is the following. Hopefully you can see, I'll go on this board. Is that A plus, let me make sure I'm proving the right thing, A plus B plus C is equal to A plus B plus C. Hopefully you can agree with me that that is true for the natural numbers. If you add the first two natural numbers and you add the third one, that's the same as adding the last two natural numbers and adding the first one. This is something called associativity. It's what a mathematician would say, but it is basically this result here. And we want to, and if we want to prove this in Lean, we would write it down like this. So the addition of A plus B add C is equal to the addition of A add the addition of B and C. And our proof is basically going to be specifying an element of this type, or defining an element of this set. And you can think of this like a game. So you have this thing on the right-hand side, which is called the tactic state. And the tactic state says we have three integers, three natural numbers, A, B, and C. And we want to prove that this result here is true. And the aim of the game is to take this goal and to prove that that is equal to true. That's what you're doing in proof. You have something you want to prove, and you want to show that that is equal to true. So how would we do this? Well, the only thing we really can do is a proof by induction, because that's the only real structure we have for these natural numbers. So in Lean, there are lots of powerful tactics, and one of those tactics is induction. So we can go induction with A. Hopefully I've written that correctly. And there are two cases. There is the case where A is 0. I'm just going to put sorry. And there is the case when, and there's a successor case. And I'll explain the notation in a second. But this is basically, if you've ever done a proof by induction, this is saying, we're going to do 0, and then we're going to do the case of n plus 1, given the case of n. So if I now put my cursor after this, where the sorry is, you'll see that my tactic, my goal, has changed. Where I had A before, I have now got 0. And if you think about the definition of addition, 0 add n is just n. So actually this thing here is just true by definition. And in Lean, that we tell Lean that, or we get Lean to check that using this tactic called REFL. I'm not going to explain what that means, but that proves the theorem for us. Now we've got the more complicated case where we're doing induction, so we're now on the n.sec case, so the n plus 1 case, given it is true for the n case. So we now have this induction hypothesis, is what you probably were taught it was called, perhaps if you did A-levels, and we now want to show that the n plus 1 case is true. And to do this may look a bit complicated, but Lean has powerful tactics, one of which is called simp. And we can just simplify this result down. And if we do that, you will see that the goal just reduces the n.sec the successor bit gets removed from our goal, and this actually becomes equivalent to the inductive hypothesis. And then to finish things, we just do exact IH, which is saying this is exactly the same as our inductive hypothesis. So that's a proof of a result in Lean. And notice that there are no mistakes in this. There are no red lines, the sorts of things you would see in Microsoft Word if you had made a typo. This tells us that this is true, and this has been checked by a computer, so there's a guarantee that you have not made any sort of mathematical mistake in this. It is a way that you can guarantee correctness of results. And these tactics, like SIMP, can be kind of powerful. For example, let's say you had three integers, a, b, c, and d, and you wanted to prove that this relation here holds. If you think about it, you can rearrange the additions, rearrange the multiplications to work out that this thing here is true. In Lean, there is a single tactic that will prove this. It is called ring, and that proves the goal for us. So we don't have to do a lot of work in general to prove these things are true. The reason this tactic is called ring is that the integers form something called a ring. Maybe if you've taken first year linear algebra, you've come across this thing called a field. A ring is similar to a field, except you don't have addition. Oh, except you don't have division, sorry. Good. So, if you didn't understand any of that, I want to tell you the advantages. I'll give you kind of the brief summary of the advantages of using an interactive theorem prover. So the one that I've kind of led this talk with is this guarantee of correctness. If you write something into an interactive theorem prover, you have an absolute guarantee that what you have written is mathematically correct. There is no way you could have made a mistake in that. You could be proving the wrong theorem, that it doesn't stop you proving the wrong thing, but it stops you proving not producing a proof of something or not defining something when you have. The second benefit is tactic automation. So, as I kind of showed you, Lean has these powerful tactics that let you prove theorems. They let you do maybe some of the simple calculations that you do on pen and paper. It lets you do that using powerful tactics. And we saw with this simp tactic and this ring tactic, it's kind of simplified the goal, and in some case, it proved that goal. The third benefit is searchability. So you can take Lean, so in the same way that you may search, Wikipedia for some sort of equations in physics like electromagnetism or something like that, those searches that Google is doing or whatever search engine you're using, those searches are based on the strings that people have written down into those documents. If you're using Lean, you can search based on the mathematical context of the definition of the theorem. So you can go, does this depend on a vector space? Does this have addition? You can search much more concretely based on the underlying mathematics of a result, not just on what the author of the blog post or the Wikipedia page happened to call it, or the notation that they happen to use when they're writing things down. The fourth thing is that everything is reusable. So we have lots of results in Lean, and all of those can be reused. You only ever have to prove things once within this project. So you kind of can build up knowledge in a way where if you do something, nobody ever has to do that again because they can use your results to prove further things. And then the fifth benefit is that things are executable. So if you've ever come across like Python or C++ or Fortran, not Fortran, whatever the programming language is called, you will know that you can execute, you can write those sorts of programs that you'd write in those programming languages. You can write them in Lean, but you can also prove things about them. You can write down definitions that are executable, and you can prove things about them. I don't know why this slide is cut off, but there's a question. Who is using interactive theorem provers? So why should you care, really? So the first people that are using them is, perhaps unsurprisingly, the mathematicians. There is a project called MathLib. MathLib is what's called a monolithic library of mathematics formalized into Lean. So it is a library of hundreds of thousands of results written into Lean, covering a wide range of areas. It was initially heavily promoted by this professor at Imperial called Kevin Bussard, but it is a library where you can find results from a bunch of different areas of mathematics. Things like category theory, you're probably not so familiar with this. Things like geometry, if you've ever taken a course on general relativity, geometry is something that comes up. Group theory, again, you probably come across this if you're in your maths this year. Number theory, representation theory, set theory, topology, so on and so forth. It's got things like linear algebra, definitions of matrices, lots of little results that you can use to do other things. Who else is using it? Well, the AI researchers are using it. And this is one of the reasons that Lean has become of great interest to lots of companies around the world. The reason is that you can have a feedback loop. You can have, maybe I can draw this, you have your AI trying to prove a theorem, and then it's sending that to Lean. Or maybe that's a bit small, let me make that bigger. And then Lean telling the AI if it's true or not. So you can have this feedback loop where you can get computers to try and prove results in maths, or if you want to do physics in an interactive theorem prover in physics, where you have this feedback loop. The AI tries to prove a result. Lean tells it whether that result its proof is true or not. It tells it whether it's made a mistake, because Lean has that power, and then the AI can take that and can use that to try and fix what it's done. So, and this has been used to great effect. In last year, 2024, Google DeepMind used Lean to get the AI to solve problems in the International Math Olympiad. They got a silver medal. They solved 4 of the 6 problems. And this year, the AIs have done a lot better. They didn't use Lean so much this year, but this kind of idea of using computers and AIs to try and prove theorems is one of the reasons these interactive theorem provers are becoming so popular. So I thought we would take a look at how this works. So earlier in this talk, I gave you this example where we defined the natural numbers, we defined addition, and then we proved associativity of addition. We basically proved that this relation here is true. We're going to see if an AI can do this. We're going to see if an AI can prove that this is true. And so to do this, I'm just going to copy this text here. And I'm going to go to one of the AIs that you can try and prove things in Lean. And this is it. This is just some of my text boxes here are kind of just portals to the internet. So this is just a web page that you're seeing in my slide here. And this is an interactive mathematical proof assistant. And let me just delete this text here. And I can put the thing that we were trying to prove earlier. And this sorry here basically just means we haven't provided this with a proof. We want the AI to have a go to try and prove this result. I'm going to give it 16 goes at trying to prove this. And you'll see out of the 16 attempts, if one of the attempts goes green, it means that the AI has managed to solve this. And we'll see how it sometimes takes a little while, but we'll see how well it does. Okay, so good. So it's already solved it in 2 of its tries. Let's take a look at the proof that it made. Scroll down to the bottom, and this is the proof. And you can see that it was kind of similar to what we did. It did induction. It used a different thing here. We just said this is true by definition. It used simp, and then it used a slightly different tactic here. But this AI was able to prove this result. Let me scroll up to the top and we can see how many cases it managed to do it. So let's just wait for this 10th case to finish, and then I can say something definite. I should say that this is a bit of a rigged example, that this proof that I showed you is pretty easy to do in Lean. So I was kind of expecting this to work. More complicated things, you have less of a success rate with AI. But this is basically the idea. The way that this AI is working is that it's trying to write a proof, and that's using the feedback from Lean to tell you whether the proof is right or not. And this is why a lot of companies are interested in Lean. I suspect the 10th case has gone into some circular argument. Yeah, okay. So, who else is using Lean? The physicists. So there is this project, which I started a couple of years ago, called PhysLean. PhysLean is PhysLean is a project basically to be the kin for MathLib, but for physics. So to basically be a monolithic library of results from physics written into Lean. And this brings me on to my second part of my talk, and I realize I only have 20 minutes left, but don't worry, the second two halves of this talk are not as long as this first part. So what is PhysLean? The catchline is that PhysLean is an open source, I should say open source, it's an open source community-run project to digitalize physics into the interactive theorem prover Lean 4. It is a project to try and write results from physics into Lean, to kind of show they're mathematically correct, but also to have a database of results that you can go to, you can search, you can see how they're all interconnected with one another. Importantly, it is community run. The aim is to try and make this a community project so that people, whether you're undergraduates or master's students or research level physicists, can have a say of what goes into the project, can have a say of the structure of the project, can contribute to it, and can help direct take the direction of the project in the way that you feel is fit. It is something called a GitHub repository. So GitHub, some of you may not be familiar with it. It is basically how computer scientists deal with open source software. It is something that you can go on and you can download the projects. You can make these things called pull requests. That is how you would try and get code into the project. This is the GitHub, this picture is kind of old now, but this is what the repository looks like. And yeah, so this is kind of the meat of the project. But there are other things and there are other infrastructure around it. Most importantly, it is a project for the physicists. So it is a project that is designed for physicists to benefit from it as maximally as possible. And that means a number of things. It is organized by physics. So it has things, so in the same way that MathLib had things like algebraic topology, category theory, these fancy areas of mathematics, PhysLean has files in it that are similar to the files that you would see, or similar to the sorts of courses that you would have during an undergraduate or a master's in physics. Stuff like classical mechanics, condensed matter physics, cosmology, electromagnetism, quantum field theory, particle physics, quantum mechanics, relativity, so on and so forth. Everything is named after their thing in physics. So, if you're dealing with the vector space of the Higgs boson, which is just C2, the complex vector space of 2 dimensions, in PhysLean we don't call that the complex vector space of 2 dimensions. We say, okay, that's the target space of the Higgs field. Let's call that Higgs vec for the Higgs vector field. So everything is named after what it corresponds to in physics. It's got physics documentation. So one of the things that you'll see if you look at physics lecture notes or physics papers is that they're written as a story. They're written as prose. If you have any friends in mathematics, you look at their lecture notes, they'll be split into definitions and theorems. That is because in physics we care about, the story behind the results. I like to call it the physics context. Whilst in mathematics, they only really care about the maths context of the result. So in physics, we have this story, kind of similar to what you'd see on Wikipedia, an explanation of why all of the results are like what they are. We have references to the physics literature where possible. So you can see there, it's probably actually quite hard to see. There is a reference to Landau and Lifshitz, this book, this series of books on, classical mechanics, statistical mechanics, etc. And let me skip over this, not so important, but our definitions are computable, which means you can, where possible, actually calculate stuff, actually take one of the functions and the definitions within Lee in the project and get a result out from that. I want to tell you a little bit about what is in PhysLean, and this is kind of the overall structure of the project. Some of this looks kind of scary. You're not expected to read this. I understand that this is blurry, so I am going to point to areas and tell you what sort of things are in PhysLean. The size of the blocks are kind of proportional to the content that they have in the project. So this big thing over here is quantum field theory. You probably haven't come across that until your master's, but it is kind of where research particle physics goes in the end. This block here is relativity, things like special relativity and general relativity, or at least some aspects of general relativity. This is particle physics. This is string theory. You probably haven't come across unless you're doing a specific master's course on that, but you probably have heard of it. This is quantum mechanics, electromagnetism, results related to space and time, units, classical mechanics, statistical mechanics, I believe, thermodynamics, some stuff about optics, and I don't know what that bottom is, thermodynamics, I think. So we have some specific results formalized into Lean. So we have the classical harmonic oscillator, and this is kind of just to show you that you can actually do the sorts of physics that you may have learned in some of your courses, that you can actually do that within Lean. It's not all just like natural numbers. You can do proper physics. So we've got the classical harmonic oscillator, and that means writing down its Lagrangian, deriving the Euler-Lagrange equations, from those showing that you get Newton's second law, and then showing that you have the solutions to Newton's second, showing that the solutions are solutions given the initial conditions are solutions to the classical harmonic oscillator's Newton's second law. We've got the quantum harmonic oscillator, probably one of the first examples you ever did if you did quantum mechanics. We've got the definition of the Hilbert space, the definition of the Hamiltonian, proofs that the eigenvectors form a basis of your Hilbert space. We've got Maxwell's equations and results related to Maxwell's equations. For example, the electric field around a point particle in 3 dimensions and 1 dimensions. We have the Lorentz group. That is, if you've done special relativity, the Lorentz group is the group that determines results of special relativity. From that, we have the twin paradox, which is this paradox that if you have two twins that start at the same point, one of them stays stationary, and the other one goes off for a trip and then comes back. The one that stays stationary ages more than the one that goes on this little trip. So we have a proof of that. We have this thing called the tight binding model. I don't know if you studied this in condensed matter physics, but it is a simple problem in condensed matter physics, sometimes used to approximate graphene in high dimensions, graphene being this magic, really thin material of carbon. The CKM matrix, which is something in particle physics. We've got something called Wick's theorem. You may have seen diagrams that look like this in particle physics. I can't draw. These are called Feynman diagrams. Wick's theorem is the mathematical theorem that is the precursor to Feynman diagrams. So we don't have Feynman diagrams quite yet, but we have the precursor to them. And we've got results in string theory. And in addition to that, we have a lot of infrastructure around the project. In particular, this is something that a guy called Justin Austin made, I believe he's called. This is a search engine for results in Lean, but it covers results in physics. You don't need to know any Lean to use this search engine, but you can search results. So you can search for results. For example, let's say I wanted to find results related to the Higgs field. I could type the Higgs field in this, and then this uses an AI to search PhysLean, and you get basically lots of theorems and proofs and definitions around the Higgs field, and an AI summary, or a written summary of what that result is, and then an AI summary. So for example, let me go down. Well, let me actually go, okay, Higgs field, minimum of potential. Let's see if we get some results related to this. You know, we get some results related to the minimum of the Higgs potential. And we could look at those and we could read the AI summary of what it says, you know, given the Higgs potential with a positive quadratic term, blah, 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 blah. You know, its minimum is this. So you can use this even if you know nothing about Lean and you want to find a result in physics. This is one way you can engage in the project. Good. How long do I have? I have 10 minutes. I want to quickly show you an example of what a file looks like. I'll be very quick with this. Oh, not that file. Harmonic oscillator, classical mechanics. So this is kind of what a file looks like in Lean. It starts out with some imports. This is kind of what you'd see in any computer programming file. And then we've got this big documentation. This is kind of the thing that I was telling you earlier about, that we want to have documentation that tells that physics story that you might see in lecture notes that you wouldn't necessarily see in a maths lecture notes or a maths paper. And then we've got results like the definition of the input data of the harmonic oscillator. That's the mass of the particle and then the spring constant. And then, you know, proving random results about, you know, the spring constant is positive, the mass is positive, the angular frequency is defined to be this thing, its square is equal to this, so on and so forth. You know, defining the kinetic energy, the potential energy, showing some results around that you can differentiate. That you can differentiate them. Results around the time derivatives of the kinetic energy, potential energy, etc., etc. The definition of the Lagrangian, variational gradients of the Lagrangian, showing that you have Newton's second law, etc., etc. Hamiltonian equations, Hamiltonian mechanics. So a lot of this is probably stuff that you learned about in your first year classical mechanics or your second year classical mechanics or maybe a short course in classical mechanics. There is some syntax here. It's somewhat complicated to see, somewhat complicated to learn, but it is something that can be learned, and we're trying to make this, you know, look as much like physics as possible and to give as much definitions and explanation as possible. Whoop, that was not the right button to click. So, I now want to talk about the last part of this talk, which is very briefly how you can get involved in this project. And I want to make it clear that PhysLean particularly needs more physicists involved. The Lean community is very heavily dominated by mathematicians and computer scientists, and this is natural because of what the program is. But we need people that have a background in physics. We need people that have taken undergraduate courses, whether that's a first year or second year. In physics, we basically need people that have that knowledge of physics. And there are a number of ways to get involved in the project. The first and the easiest is to join the discussion forum. I should probably have put a link here, but I didn't. So the discussion forum is something called the SULIP. I can probably go onto it. The website is leanprover.sulip.com, and there is a PhysLean channel within this. And this is where conversations about the project happen. It's where we kind of discuss what's going on within this project and this discussions about, you know, the classical harmonic oscillator, things about cosmology, things about the unbounded operator. So if you want to get involved in the project, that's kind of the first place to start. Ask questions, get involved in the discussion. We need more physicists. We need people that understand the physics background, etc. Oh, I keep pressing the wrong button. I apologize. You can have write documentation. This involves no lean stuff, but one of the things we're trying to do in the project is write better documentation from the point of view that a physicist can understand. So I'm going to show you the file that you saw a second ago. This is what that file looks like on the website. It kind of compiles into hopefully something that is readable. You scroll down and you can see it's kind of, the aim is to structure it like you perhaps would see some lecture notes. This may be a bit confusing, all of this notation, but we want to improve this story, this documentation that goes around it. And if you've got a background in physics, how can write this documentation? How can improve this? Even, for example, you know, improving the overview of the classical harmonic oscillator, which is currently 2 lines, which isn't great, is a contribution. And this is, you can think of this as like a research level project. This is something that you contribute to the project, it's going to grow, it's going to help people in the future, and you know, every contribution to the project is tracked by GitHub, so you kind of know who wrote what. And yeah, so it's a good way to, if you're interested in perhaps helping out with some active research, this is a good place that you can get involved. You can help write informal definitions and lemmas. So within PhysLean, we have these formal definitions, which are kind of, and these lemmas, which I kind of showed you earlier with the natural numbers, but we also have informal definitions. And these, so this is an example of the Hubble constant. I think it's a definition of the Hubble constant. It's just an English written definition of the Hubble constant and some random syntax, which, you know, is easy to write. And if you ever struggled writing that, I would help or someone would help. But it's splitting the results that we have in physics down into little definitions and theorems that somebody at some time could come along and formalize. This is a massive help to the project, to the community, because we don't have these expertise in physics that you all have because you're doing a degree or an undergraduate in physics. There's a lot of, like, writing this sort of stuff, you can do it with your undergraduate in physics and contribute to the project. And all it really entails is taking perhaps some lecture notes that you have, perhaps you pick a book, your favorite book on physics, and you split it into definitions and theorems, and you add it to the project. There are, you know, tutorials on the internet about how you can, how to actually contribute to the project, but worst case scenario, you just ask on the discussion forum or send me an email. And then if you really want to get involved proper, you could try formalizing stuff. You could try and learn what on earth I was writing out at the start of this talk. You could learn, you know, what Lean is all about in terms of the code, and you could take a look at the to-do list or ask on the Sulip. Yeah, so that kind of concludes my talk. So I'm happy to take any questions if people have them. And yeah, thank you. Yeah, I just feel like, yeah, I don't know. Yeah.
I've got a question, is that I guess it's more of a practical question, like,
yeah.
So there are a lot of existing physics results, right?
Yeah.
But doing this formally takes a lot of effort and takes due understanding of the work, but you do not get any credit for it whatsoever. If it's correct, right? You only get, only if you prove that it's wrong, and then
so formalize it, at least in the maths world, the concept of formalizing stuff is seen as an additional step. It is seen, people do get credit for it, people do write papers on it. It is seen as new research. It's not just like taking a document written in English and translating it perhaps to French, or taking something in French and translating it into English. It is seen by the community, at least in mathematics at the minute, as very much something that is new, something that is active. Because in general, when you're formalizing stuff, when you're writing stuff into Lean, you really do have to think about how do you do it? How do you, how do you, it's not, I'm not going to pretend, formalizing stuff is easy. It is difficult, and you do have to think about how you do it, if that answers your question.
Can these two output some readable paper like LaTeX did?
Yep. Yes. So there is this thing. Let me go over. So the PhysLean has a website called PhysLean.com. There is this thing called Verso. This is not so well developed. It became kind of complicated to develop, but you can write. So we've got something for the classical harmonic oscillator. You can write things that look like this, and you can use Lean to do this. And you can write this in such a way that Lean knows what things are. So if I hover over things, you get things that are like, this is a real number. And this is kind of one way that you can take Lean and you can hopefully write papers with it. And people write books and things like this. But yeah, and then the documentation that I kind of showed you earlier, which is down here, is kind of an attempt to, don't know why that's done, an attempt to kind of replicate what you would see in some lecture notes, to try and write enough, English there that you would be able to follow it along without having to know Lean necessarily. Yeah, I think.
I was wondering what kind of capabilities do you think can be unlocked by like kind of training large language models on data like this compared to regular text?
Yeah, there are lots of startups and lots of companies that are trying to do this. They're trying to basically do, that demonstration I showed you. They're trying to do that, and they're trying to take results. They're trying to fill in proofs into Lean, and we're getting to the stage where these are kind of getting impressive. They can do things that you naively would think is quite difficult. And I think, it's hard to predict where that's going to go in the future, but there are lots of people putting a lot of money on using Lean to use AI to do things.
Do you think it will lead to kind of an increase like quantitative intelligence in this field? Like it'll be able to like kind of think of new ways of solving problems, or do you think it's just kind of like the proof checking thing where like the reasoning models are already quite good at doing that, like checking their own work?
You're kind of asking, will it produce proofs that we've never heard of, never seen before, or results that we've never seen before, rather than just reproducing what we have already? Is that kind of what you're asking? Okay. Yeah, I think this is possible. I'm trying to think of an example off the top of my head where this has happened. I know there have been examples where, ChatGPT has proved a result that we didn't know was true before, or we didn't know was false before. And, they've taken that result and then they formalized it into Lean to make sure it's correct. So we are getting to the point. And having this data, having this structured information in this way so that the computer can read it, is obviously helpful. Like, if you're having something where the computer can read it and obviously it can read back in the same language, and then you have this guarantee of correctness. But yeah, I'm not going to pretend we've seen, no one's produced new physics using AI and Lean yet, but there are startups working on it. Google DeepMind is working in this direction. There's a company called Harmonic, not in the physics direction, but in the mathematics direction. Yeah, there's lots of money, there's lots of investor money. I think up there was.
So picking up on your point about the fact that physicists like context and
Yeah.
other factors behind discovery, how much potential do you think PhysLean has for incorporating that? Because the problem with physics is some things are true sometimes and not
Yeah.
true other times. So
Yeah.
I guess, like, for example, you mentioned the classical harmonic oscillator.
Yeah.
As a physicist, as well as thinking like what proofs involved in that, I'm also thinking, can my molecule be correctly approximated as a classical harmonic oscillator?
Yeah.
In this case, in this temperature regime,
Yeah.
responding, that kind of thing.
Yeah. So the way that I like to think of this is, if it has a mathematically well-defined formulation, then you can do it in Lean. That doesn't mean it has a mathematically well-defined justification. It's slightly different things. So a well-defined mathematical justification is what a mathematician would want. That's like, this is justified because of this, this, and this. a mathematically well-defined formulation is what a physicist would do, which is like, let's set this term to be equal to 0. Let's take temperature to be less than, let's take the limit as temperature goes to 0. You know, you don't have a mathematical justification for that, but it's mathematically well-defined. You can do that mathematically, if that makes sense. So I think a lot of the things that, like, the sorts of examples that you get can be done in this language. You just can't justify it mathematically because you can't justify it mathematically on pen and paper. But you can do the steps that a physicist would take to get to the answer, if that makes sense. There are some things where it's slightly more tricky. An example is certain approximations. So physicists, oh, I have to go down. So physicists, you know, may be happy approximating 1,200. They may be happy saying that that's approximately 1,000. And they may be happy saying 800 is approximately 1,000. But they wouldn't be happy saying 800 is approximately 1,200. So that sort of stuff becomes slightly more tricky. This is a famous paradox in philosophy where you go, you know, you have a heap of sand. If you take one particle of sand out, it's basically still a heap of sand. You can take that to the limit where you've got no sand left and you've still got a heap of sand. So this sort of stuff is slightly more tricky to do, but in general, I think a lot of the approximation type stuff, a lot of the things that physicists do can be done in this way because they have mathematically well-defined formulation.
But like even not just approximations, like I guess like a really simple example, if you're doing like, if you want someone to apply it to a particle physics research paper,
Yeah.
is it going to flag up E equals PC in like a ultra-relativistic regime, or is it going to say E equals gamma C squared like that?
This depends on what your starting point is, right? This depends on what assumptions you put into the starting point of the problem. All of this formalization stuff is like, it's true given that you set the problem up in the right way. And you may want to set the problem up non-relativistically, or you may want to set it up relativistically, if that answers your question. I'm happy to speak after as well. Yeah. Any other questions? I think you were next.
On the big graph you showed with all the areas,
Yeah.
did you see a lot of buy-in from certain areas of physics?
Yes.
Others?
Yes.
So the optics box, for example, is
Tiny.
tiny.
Yeah. Yep.
It's at the far right corner there.
Yep.
In rethinking. So I guess I'm kind of curious. Does that indicate that there is a differing need across fields of physics?
So the distribution of areas in this graph is simply a distribution of community interest of people that are currently working on PhysLean, rather than anything about is this more formalizable than anything else. It is simply that we have less people working on things like thermodynamics and optics, and less like, not necessarily less people, but less time that we can spend doing that. So if things like optics or thermodynamics or statistical mechanics, these things in the bottom right-hand corner are things that you're interested in, you know, there's nothing stopping people working on that area. It's not like there's a technical gap where these are not done. It's more, you know, my personal research is quantum field theory and particle physics. So this more shows you like what's currently in Lean, basically because of the community behind it, not anything technological, if that makes sense. Yeah.
What subfield of physics do you think PhysLean will first help push the frontier of either because of maybe better AI reasoning models or able to derive new proofs, etc., or maybe humans use it to help?
Yeah, this is hard. Yeah, I don't know. I'm tempted to say quantum field theory and particle physics, but there are lots of people working on that direction, like in pen and paper, and it's really hard to push forward anyway. I think more likely it's going to happen in one of these smaller areas that are currently less developed, where you have more, let's say, interesting results about, so like quantum field theory is about the structure of the universe, and obviously it's harder to do something original in that area than elsewhere. I should say though that there is research level, like there are new research level results within PhysLean. There are results that are not in any publication. So you absolutely can, do new physics in this project. It's not, I kind of presented it here like as in, we've done like the classical harmonic oscillator, we've done this and this and this. But there is also the other side of it, which is, I'm working on a string theory paper with people that contains new results from physics that haven't been seen before. We've got stuff that I did during my PhD on, stuff related to quantum field theory, that this is in there. So it's not restricted, it's not kind of restricted to these undergraduate projects, if that makes sense. But obviously that is the place where we would like help. Yeah.
So it's like, I was a bit unclear. So you're saying that you can just take a research paper and that has maths in it, and then you can just input that into the hypothetically.
Hypothetically,
And
yeah.
So I had a quick look, and it didn't look like there was a lot of research papers.
Oh, yeah, so we're not, so, okay. When we don't organize it. We don't organize it by going, we're going to formalize this paper. What we do is we go, we want to formalize results related to string theory or electromagnetism. We follow the approach of a computer scientist. And the approach of a computer scientist is to go, I want to formalize results related to lists or something like that. And then they prove everything they know about lists, or then they define everything they know about lists. So the same thing here, we will prove, we will give Maxwell's equations, and then irrespective of what we want to do with Maxwell's equations, we will take that and we will prove everything we want to know about Maxwell's equations. This is called making an API, slightly different from the other use of the word API, but it's kind of like this philosophy where you don't go after a single target, you don't go after the result of a paper, you kind of want to build the foundation so that other people can come and bring and use that results from there, if that makes sense. We're trying to build a library of results that other people can use, not just results that get you to a single target. But there are definitely within PhysLean those targets that are from papers. They just happen to be as part of a distributed system of lemmas and results.
So would you allow someone to say, if they're interested in doing my paper,
Yeah.
would you allow them to put that on?
Yeah, absolutely. That's definitely, yeah. Again, this is a community project. So if people came in and they said, I want to formalize this paper, it's absolutely valid. We would probably ask for it to be done in, split into the results to be put into their appropriate places within the project. It just helps maintaining it, if that makes sense. But if you're after a specific target, so be it, this is kind of what I did. It's formalizing something in string theory. We had a paper, we wanted to formalize it. We had a goal that we wanted to aim for, but we wrote it and we did it in a way that kind of mirrored the sorts of things you would see in an open source project or an open source library. And there's a benefit of doing that, and the benefit is you write better code, and you write code that more people can use, and you make less errors, and it's just easier to work with, if that makes sense. Yeah.
So there's this argument that's very common in physics, which is that you assume that something is small, and then afterwards then you prove that it is small.
Yeah.
But evidently this is the circular argument, right? But nearly 60% of physics uses this. Then is there
Is there a way to do this?
what is the I guess what do you guys do?
Yeah, okay, I don't think there's a specific example of this in the project, but it goes back to my answer to that, which is this sort of argument, not mathematically justified maybe, but mathematically well formulated, right? You can set a term to be small, you can solve the equations with that term to be small, that's fine, you know, that just says, let's ignore that term in this equation. We get the result, and then, you know, you plug it back into the equation. You can do that because it's mathematically formulated, and Lean lets you do that. You just have to give that story. I mean, you'd have to give that story behind it that you would see in a physics paper, which explains sort of why you're doing that. And obviously you can't put that justification, because it's not a mathematically well-defined justification, you can't put that within the theorems and the definitions, but you can put that in the documentation, and you can put that in the other information that goes around the file.
So this is just an associated question. It
Yeah.
feels like there's a lot of these things that cannot be compressed into just proofs. Like,
Yeah.
which, like, for math, you could just, everything just proofs.
Yeah.
But for PhysLean, there's like these things that you have to insert, that, like, numbers, ordering that you have to insert. Do you mean from the approximation point of view, or you mean from like experimental data type of thing? Like from a user point of view, that's
Yeah. I mean, you have to do this. You have to do this in mathematics, right? In MATLAB, you have to define a vector space. You have to take the definition of a vector space and run with it, right? You have to prove theorems about that. The same is true in PhysLean, where you define something and you run with it and you prove results about that. Another approach to this sort of project would be to try and axiomize things, which is to go, let's take a unified starting point from physics and try and derive all results from that. But we don't know how to do that. We don't know how to do that anywhere near on pen and paper. Like, this would be like not a grand unified theory, a theory of everything, right? And we don't have one, and it's highly unlikely we will have one anytime soon. So this is kind of not the approach that one could take that approach and see how far one gets, but then you're limiting yourself massively to what you can do, if that makes sense. Yeah.
I think that concludes our talk today. If there's no more questions, thank you, Joseph, for your talk today and for inspiring many of us here. Thank you for everyone for joining us today. I hope you enjoyed the talk. Please feel free to come down and ask Joseph further questions you have.